Alrighty, this is section 7.1. This is a dot product. Now we already have seen the dot product mentioned and so forth, and in their case they are only showing it for 2 dimensions, but we'll mention it for n dimensions. So if we have a vector x that's equal to x1, x2 up to xn, and we could say transpose. It really, the vectors could be row vectors or column vectors, and then y is some y1, y2 up to yn. We define the dot product between those as x1 times y1 plus x2 times y2 plus all the way up here to xn times yn. And so that's the sum I equals 1 to n of xi, yi. And that's our dot product. Now it has properties. Again, we've kind of seen these properties, but so property 1 is a distributive property over addition. So if I have x dotted with y plus z, that is simply x dot y plus x dot z. It's commutative, so x dot y is equal to y dot x. 3 scalar multiple. So if I have t x dot y like this, I can just take that t out and call it t times the dot product of x and y. And of course I can move that t over to the y because using 2 up there to swap things at this point, so I could swap the x and y at this point and then reassociate the t with the y, and so I can put the t on either vector. If we take x dot x, you see that's x1 squared plus x2 squared plus xn squared. So we could also write that as the sum I equals 1 to n of xi squared. But then also notice that that is the square of the magnitude of x. So if I take the square root, so what that means is the magnitude of x we could write as the square root of the dot product of x with itself. And finally 5 is that if these are column vectors, then we could think of this as x transpose y. Or, for that matter, y transpose x. Because that's a real number, so it really doesn't matter which way we do it, plus we know we can swap things around with that. Now, so for some of these, I'd say 4 is pretty darn obvious and so forth. A proof of something like, say, 2 pretty much the proofs of these, excuse me, all really boil down to the real numbers. Proof of 2 is, so if I have x dot y, then I can write that, we know, as I can write it out, or I can write the sum. So I'll write it out this time, x1 y1 plus x2 y2 plus all the way to xn yn. Well, now just use properties of real numbers and swap the x's and the y's. So I've got y1 x1 plus y2 x2 plus all the way to yn xn, and so that's just y dot x. So these tend to be kind of straightforward as far as proofs. Now, before we get into the geometrical meaning of the dot product, as far as their little proof for the two-dimensional case, what I want to do is mention that the dot product is one example or one case of an inner product on a vector space. And so an inner product, whoops, that's not what I want. What just happened here? There's a triangle inequality. Oh, dot product. Not sure how what I hit to make that disappear, but anyway, so it's one example of an inner product on a vector space. And really, you know, what's an inner product? Well, actually, an inner product is simply a function on your vector space of two vectors that satisfy these types of properties. Whoops. Okay, go back to the writing mode. Okay, whew. It's, well, really the first three properties here. Okay, so if I have something that does this, then I can call that an inner product. So, for instance, on the vector space of integrable functions, okay, on the vector space of integral functions, say on the interval 0, 1, if I take angle brackets like this, often that might be our inner product. The way we talk about an inner product, it might be angle brackets like that. I can define that as the integral from 0 to 1 of f times g dx. And that is a perfectly good inner product. And so, you know, if you look at that, remember those first three properties, certainly I can distribute that over addition. It doesn't matter what order I write the f and g in, and if I have a constant multiple, I can take it out. Right, so, you know, if I have something like f inner product g plus h, that's just the integral, according to this definition, f of g plus h dx, but we know we can distribute that function over the sum, So that's fg plus fh dx. And we know we can break up that integral at the sum. So we have that one plus that one, fh dx. And so now that is f inner product g plus f inner product h. Okay, I wanted to show that idea because of now the geometric interpretation or geometric meaning of the dot product. And what we, I did it again. I'm not sure how I'm doing that. What we have is that, oops, and again it went to off the writing mode. Mystery. Okay, so if I take x dot, oh, and this is theorem 7.1.2. So this is x dot y. This is the geometric meaning here is that this is the magnitude of x times the magnitude of y times cosine theta. And where we're drawing the vectors from the origin. Okay, so here is my x vector, here is my y vector, here's theta. So this theta is the angle between the vectors. Okay, so and so we can interpret x dot y as this magnitude of x, or the length of the x vector times the length of the y vector times cosine theta. And so now I'm not going to go through their proof. They use a law of cosine, so you know they end up making this triangle and showing that using the law of cosines, that x1 y1 plus x2 y2 ends up being that. Okay, so that's their proof, and they just do it with these triangles. So they would call this O and that A up there at that point, and that one B. So if you look at their proof, that's what they're doing, and they just use law of cosines here with this thing. Okay, but now because of that, you know, they show it for 2 dimensions, but actually what we do generally in vector spaces with that inner product is we define cosine of theta for theta, the angle between 2 vectors. Okay, so actually in many vector spaces we just define this. We just say this is what we mean by sort of an angle, but really in terms of cosine of the angle. And so between 2 vectors f and g. Now, and I'm using f and g not because it has to be the integrable functions or whatever, but to point out it's not necessarily even Euclidean space of x1, x2, x3 up to xn. You know, not it doesn't have to be n-dimensional Euclidean space. We just define cosine theta to be, cosine of theta is equal to the inner product of f and g divided by the inner product of f with f square root and square root of inner product with g and g. So you see what this is doing with our dot product. This would be an x dot y over the magnitude of x times the magnitude of y, which is just, you know, what this geometric meaning up here is saying. All right, just divide the left-hand side by the two magnitudes, and we get cosine theta is equal to x dot y over those two magnitudes. And so it is the case in Euclidean space that this quantity really does measure cosine of theta between the two vectors. However, we could choose to ignore that real live fact and just simply say that for any vector space, we're defining cosine of theta for that angle between our two vectors to be this inner product sort of thing, which would mean then for dot products it's this. Now, that's why we define it this way. Is the inspiration, of course, came from real live Euclidean space, and in particular in 2 dimensions, but this works in 3 dimensions, 4 dimensions. You can still use that law of cosines idea and get this. So you know, so this is way bigger than just our two vectors. And I think that's something to take note of, is that, yeah, we are doing this dot product, but more generally, we could be talking about an inner product, and those inner products have these same sort of properties. And so we can actually talk about the angle between two vectors that are not arrows in n-dimensional space. Okay, so that is the dot product and the inner product, and our geometric meaning for that dot product and inner product.